I'm going to critique two labs. I've got two samples here, and we're going to go through and contrast them and see how they differ and what you can do to fix your lab. So hopefully you've got your acceleration at an Incline lab out, and you want to take some of the critiquing I'm doing here and use it to make yours better. You're always trying to look at what level are you at and how can you move to the next level. Okay, so this person doesn't have a question at all. They just copied the task. Now, having the task is good, but it's better to word it as a question. So this is a better way to put it. Methods and materials. This person starts with a list, but it doesn't say anything about how they prepared the track. Look at the difference here. I set up a track propped up on one end by 4 textbooks. So this is a lot more descriptive and takes the same amount of words. Okay, so if you look at this versus this, it literally is the same number of words, but it's a very different way of using those words. I set up a meter stick on the table. For reference, very important piece of information. The meter stick is not mentioned at all here. And I filmed a video of the cart being let go at the top of the track and let it roll down to the bottom. So it said what is actually happening here. Here, it says after, it is important to line up the camera parallel to the experiment. This is really important, and have all experiments be within the frame of the camera and keep the camera steady. So this part here is very important, and I would add that to this other one, right? That's a good piece of information. Both of these are missing any sort of labeled sketch. So you can hand draw a sketch of the situation. You can take a picture and label it using the drawing program or text boxes or however you want to do it. But you do want to, this picture here is data collection. It is not a labeled sketch. So that's something that both need to add. However, this person did not include any data. This, what they're calling data, is actually the class data based on everybody's analysis. So this doesn't even belong here. This, where it goes is in the analysis section and labeled as class data. So this person actually has no data. Whenever you're using video capture and tracking, you need to include the tracking. The other thing that you want to do is you want to make sure before you take a screenshot that you make the calibration tool and the axis tool visible, then take a screenshot, because I want to see, because that's often where there's problems and I need to understand what you're doing when you're doing it, okay? Both include their graph. These are fine. You know, I probably would have encouraged this person here to omit this last point by using a highlighter. You'll also notice that this person there, they got rid of the uncertainties while this person left the uncertainties in. It's not that it's wrong, it's just more confusing, so I highly recommend you delete that. And then this person has this narrative. Not important. I would omit all of that. There's nothing in here that's important at all. There's actually some things in it that's wrong. So I would get rid of all that. Here is where this person included the angle data for their group, just for other people who had the same values. Whereas here, this person included all the angles, which were not needed. I have no idea which angle this person actually did, because there's nowhere, I didn't notice anywhere where it was mentioned, so I don't even know what data we're referring to. So this is really not a useful thing to include. On this side here, you'll see that there's an equation of the trend line, an R squared, a mathematical model. All of this stuff should go, I would put it underneath, right under the graph, so we know what it refers to. So the equation of the trend line, I would just do this, comes out of this box, and then you write it in the form y equals mx plus b. The r squared value is what tells you, you know, this is not really necessary. You don't have to do that. It's not wrong, but you don't need it. So you can put that. You don't have to rewrite it, but you can. And then you've got your mathematical model. The mathematical model is the next step after the equation of the trend line. And all you're doing is you're taking, let me just grab a pen. You're taking what's actually on the y-axis and you're plugging it in for y, and you're taking what's actually on the x-axis and you're substituting in that word for the x. So you'll see you got velocity equals 1.16 times time. So that's the only difference. It's the same exact equation otherwise. But this is really great evidence for your CER. So this is really what you want to work on adding to your analysis as the next step, okay? All right, so these calculations, I do not need to see calculations for averages, so don't worry about showing that. I trust that you know how to do an average. There was actually no calculations for this in this particular lab. So let's talk about sources of experimental error. First of all, source of experimental error are part of analysis. I would take that and put it before the CER. The CER is the very last thing that you do. So we're gonna, for both of these people, this would go in that order. So it says, this lab was pre-done by a host. When the host let go of the cart, you could generate some force. So this is not a good source of error, because you want to, first of all, talk about this as if you're doing it, not as if I'm doing it. Because remember, we're in a weird situation right now, but you have to understand how the experiment was set up. So you're going to have to put yourself in my position when you write up your methods and materials and when you're doing the sources of experimental error. So you want to talk about this as if it's something that you actually perceive and did. So could I have generated some force? Sure, but unlikely, and it would not affect the acceleration, only the initial velocity. Also, it says, since we used capstone to track the object, some students might have clicked a different starting point than other students. Again, this is irrelevant. We don't care what other people did. I only care what you did when you were collecting the data. So there are two sources of experimental error here, but neither of them are relevant, okay? This person's the camera had to be perfectly parallel to the direction of motion of the cart. Tracking is based on judgment, which may be off. Placing axis and calipers are based on judgment. Those are all fantastic because those are limits based on the type of methodology we use, the tools we're using. Those are all really important factors that would then change your results if you did it wrong or differently. And you can't really do much about it because they're all judgment calls. And these three actually are true for every single time we use video capture. So they're great. You can explain them a little bit more. This is kind of like just very superficial treatment, just naming them without explaining like how they affect, but this is the start for sources of experimental error, okay? And then the CER. So let's take a look here first. The acceleration of the cart was 1.39 meters per second squared. So he names this, but there's, I mean, I see he's pulling it from his graph, but I don't really know where it came from. But that's a good claim. Here, sorry, this is not a good claim because this says determine the relationship between velocity and time. I didn't ask for acceleration here, so this doesn't even answer the question. So since this doesn't answer the question, then this is not an appropriate claim. He writes a conclusion, but nothing, like if you don't address the question asked, then it doesn't matter what else you write after a wrong claim. Okay, so we're not even going to bother reading all that. So then if we look at this one, the relationship between velocity and time for a cart rolling down a track is constant. Okay, is constant acceleration. This person also, while they focus on the question, they also mention acceleration. So these two people got the same exact score on the arguing a claim because neither of them addressed the actual question. This should say, let's go through what it should say. The relationship shown here is direct. There is a linear relationship, so either one. So you can say is linear, or you can say it's direct. I prefer direct generally, but that's fine. That's it. You're going to look at your graph. You're going to look at the equation of the trend line. Now, once that's fixed, this is awesome evidence. So the relationship is, so the mathematical model for this relationship, we don't need any of this, is velocity equals 1. So this is just copying the mathematical model and inserting it here. The r squared value, then names as r squared value, and what that means. So 0.859 means that 85.9% of my data points fit the trend line. So this is important also. So this is fantastic evidence. So this is very powerful. It's proof. Why is this proof? Oops. This is great proof because if I'm going to say something's linear, then I should have a linear trend line. Right? If I'm going to say there's a direct relationship, then I need to see that you have a linear trend line. So seeing that velocity is on this side of the equation, time is here, and you've got a slope, that communicates exactly that feature. And it's really concise, it's very analytical, it's sophisticated. These are all the qualities we want in our evidence. So then, the slope of a velocity time graph is change in displacement over change in time, which is equal to acceleration. So this is a mistake. This should say change in velocity. So that was just a typo, over change in time, which is equal to acceleration, which I would even say is the definition of acceleration. Because we only use constant acceleration, I knew to use a linear line. Yeah, you don't need this at all. So you just want to state the theory and tie it back. So we don't need that. The acceleration of the cart was 1.5. And so the other thing you can do, the average acceleration between us four was 1.23. This is fine, mentioning what the average acceleration was from the value here, from your group values. That's a very strong tie showing that you were really close to the others who had the same video. So what we've got is you've got the first part of your reasoning statement is here, right? That's the physics, and then here is proving that your value matches the physics. So there's two parts to the reasoning. This now, in its current form, is actually expert level. Well, maybe a little, maybe it's actually advanced. But it's really close to expert level. We're not quite ready for that yet. But this is what you're shooting for. But if you can't write a good claim, then nothing else is going to really matter. So work on the claim, work on your evidence. We can work on reasoning later. Do it in that order. If you have other questions, please let me know. There's one other thing I do want to mention. I want you to notice these annotations, right? So this person is annotating, showing me what they changed since the last lab they did. Okay, so what are they fixing? So this person didn't do any of that. So this is using feedback. This person is just pointing out what they changed. The next step for them is going to be, why did they change it? So why did I omit the description of the data correction? Why did I use capstone instead of a data table? So that's the next stage in improving this particular lab. So you're not going to be able to make all these changes at once, but you can start working towards any, 3 or 5 of those changes. And again, if I can help you make those improvements, please be sure to make an appointment with me, and I'd be happy to talk it over with you.